So they have sealed the doors now. It's too late to escape. So you're stuck here with me. And just to annoy the lighting guy, I'm going to stand here for my introduction. Skip past the test slide. Okay. Do we only use 10% of our brains? Well, here's some spoilers up front here. It's a popular idea. We've probably heard it many times before. Unfortunately, it's not true. We have actually done experiments so we can see all areas of our brains are activated when we're performing any sort of activities. But are there ways that we can make much more effective use of the brains that we do have? And to that, the answer is definitely a resounding yes. And there's lots of different techniques and approaches, some of which you're probably familiar with, to do so. It's been a big area of interest of mine for many years now. In fact, the first couple of talks I ever did at this conference, so over in Oxford in those days, but they were all about some of these techniques. And some of them have got a lot more mainstream in the intervening years, so I don't talk about them quite as much anymore, but I'm still really interested in them, still learning new things. Something else that I've been really interested in for a few years now is testing and TDD, particularly in the context of C++, but in general. So I wrote a test framework a few years ago, Catch, now Catch 2. I know some of you will be familiar with that. And in recent years, I've also been doing training in TDD. So I'm now fully independent, so if any of you need TDD training, do let me know. But the last couple of years, I've started to realize that there's actually quite a big crossover in these two areas of interest. And I've been trying to really formulate or gather my thoughts on this to put it together into a cohesive talk. And finally, I think I'm ready to do that. And that's what this talk is. This intersection of the psychology and neuroscience of productivity and TDD and how they work together much more effectively than they really should. That's what I want to talk about today. Hence the title, Rewiring Your Brain, with test-driven thinking. Not just development, but the whole thinking process. And in brackets, in C++, because we're going to have a code demo, that's in C++, but that's really the only thing that's specific to C++ about this. So, before we get started, just to introduce myself, I'm Phil Nash. That is my, what do we call it now, X handle. I'm actually never on there, so probably don't use that. I've got my Mastodon handle as well. And this is now my company, Shaved Yaks. Did I mention I do training? Let's start right with the fundamentals. Talking about testing, why do we write tests? We say we should always start with the why. So I'm going to start with the why, but actually I want to start by taking that off. Go even more fundamental. Do we write tests? And maybe I can ask this question of the audience. So who here says that they regularly, as part of their development activities, writes unit tests? So that's a pretty good number. I'd say more than 90%. It's usually closer to 50, 60%. So good self-selecting crowd. But, okay, how about this one? Who thinks that they should probably write more tests than they currently do? All right, similar number. And that's usually the bigger number. But why do we write tests? Or, to flip it around, because you just said you should write more tests, then why do we not write enough tests? What's stopping us? We think we should, but we don't. There must be a reason. There's actually lots of reasons or justifications that people have for not writing enough tests or not writing as many tests as they think they should. It might not be the same thing. I'm not going to put up all of them. I just want to pick a few that maybe will resonate with you. These are ones that I commonly hear. For example, maybe you just think that writing tests is extra work. I'm sure many of us, most of us have had that thought. Some point or another, a lot of people, that's their definition of testing. It's just extra work. I've written this code, I've seen that it works somehow. Well, set aside whether that's actually a test or not for the moment. I've seen that it works. Now I'm going to write some extra code to show the same thing again. That's extra work. Okay, that seems fair. But if it's extra work, that's going to slow you down because you're doing more stuff. And one of the reasons it slows you down is because it actually distracts you from the thing you were doing in the first place. You were trying to write some code to solve this particular problem that was motivating, and now you've got to switch your mental frame of reference over to how to actually test it. Maybe even like writing that test in a different language, or at least a different approach to writing code. Or maybe we just think that testing is boring. That's not what got us interested in this in the first place. Particularly if we sort of came up as like a hobbyist programmer. I know many of us did. You know, we get that buzz out of just hacking some code together, seeing that it does the thing we wanted it to do, and then moving on to the next thing. Testing's not like that, is it? Let's say there are many more reasons. We're going to come back to these ones in particular. But let's put that aside for the moment. Come back to this question. Why do we write tests? Put up some reasons that people give for not writing tests. So why do we do it then if it's got all these problems? Put the emphasis on the do. Again, I'm going to give a whole set of reasons. These are by no means exhaustive. And in fact, as part of my training, I ask this as like a flip chart exercise, and I get people to call them out. And I have a whole page, and I run out of room. And there's always some that I hadn't thought of, and I've been collecting those over time. So this is not my complete list, but just want to give you a sample. Perhaps the most obvious one for most people is we write tests to catch bugs. And certainly that is an important use case, perhaps the first one that we come across. If that was the only reason, then you could see, well, you know, there's a diminishing return there. Is it worth the investment? Catching bugs is great, we want to do that. But there's a lot more to it than that. So how about this one? Maybe this is a slightly different way of thinking. We write tests to encode our expectations. We're thinking, right, this is what I expect the code to do. Write that down in a way that can be verified. We've encoded that expectation. This is going to turn out to be really important later. So watch for this one. Maybe closely related to the first one. We write tests to catch a regression. Maybe we caught a bug some other means. Maybe it's reported by a user, or you just stumbled across it yourself, and you think, oh, I'm going to write a test for that to make sure once I fixed it, we never see it again. But actually, even tests that have never failed, they can still act as regression tests in the sense that once you've got a body of tests, you can make some changes over here and see, oh, did I break something that I wrote earlier? That's a type of regression test as well. So that's a really important use case. Good. Sure we're familiar with that. What about this one then? This one tends to divide the room into two, not necessarily literally, but for some people they think, well, what have tests got to do with documentation? Or you might be the type of person that thinks that's the most obvious thing in the world. How often have you heard someone say, if you want to learn how the code works, go and have a look at the tests. That shows the code actually working. This is how you're meant to use it. And the great thing about using tests as a form of documentation, developer documentation, is that they don't get out of sync, unlike just about every other form of documentation. Because if they do get out of sync, they break. So the code tests the test, the test tests the code. Works both ways. There is a flip side to this, though. It's a double-edged sword, because not all tests that you write are really how you want people to use your code. You may be like probing at edge cases and the dirty underbelly of your code. You just want to make sure that it actually survives that, but that's not what you want other people to be doing. So if you're going to use tests as documentation, do try to have some way to separate out those two ways of using it so that you can point people to the right place, so that it's obvious when they get there. I won't talk too much about how to do that today. But this is just a sampling of some of the many advantages of writing tests. I'm going to put a few more up. Again, still not exhaustive, but I won't go through these all individually. What I want to point out here is that all the ones on the left that I put up here, well, we can get these benefits from writing just about any type of test. Many different types of testing. I'm going to focus a bit on unit tests today, but there's many others. And you'll get these benefits from all of them. The ones on the right are really much more specific to doing testing in the context of TDD, test-driven development. Again, not exhaustive. These might look a bit odd, and we will actually dig into most of these a little bit more through this material. The point is, there's a whole set of benefits you're not getting if you're not doing TDD, even if you're testing. Before we get to that, and come back to this set of excuses or justifications for not writing tests we looked at earlier. Extra work slows you down, distracts you from what you're doing. A little bit of a spoiler, but just to give you an idea where we're going. What if I was to say to you that instead of testing being extra work, it would help you to avoid rework? I see Dom nodding enthusiastically here. Such that over time, and maybe sooner than you think, you would have done less work overall. You know, how much time do you actually spend redoing things, fixing things up after the fact, or just working around a bad design? Yeah, save you time in the long run. What if I said to you that instead of slowing you down, it could actually speed you up? For similar reasons, but some more as well. We'll look at these later. What if I said that instead of distracting you from what you're doing, they could actually keep you focused on what matters the most? And this is one thing that I want to dig even deeper today than you might normally hear. And of course, what if I said instead of testing being boring, it was actually fun? Yep. Believe it. We'll get to that. Okay. I mean, this all begs the question, you know, how are we going to prove all of these things? We will get there. And the main way we're going to get there is by looking into the psychology and the neuroscience of how these things work. First time I did the version of this talk, I was told that talking over this slide was very distracting. So I'm going to move on before I carry on. I tell you that one of the most important fundamental principles we're going to be basing all of this on today, something very simple that I'm sure you're completely aware of, but just keep this in front of our minds because it's really going to make things easier. The human brain is a big association machine. It's all about the connections, the neurons, pathways. If you can connect things together, then it's not just about memory, but it's also about accessing different mental resources, putting you into a different frame of mind, being able to work in different ways. It's actually a really powerful concept that we're going to be looking at again and again. This is really the fundamental of it. And we're going to look at 3 areas. One is habit forming. And why is this relevant? Well, let's assume I've convinced you that TDD is going to solve all of our problems, and you know how to do it. You go away and you think, wake up, like come out of the matrix thinking, I know TDD. But then you've actually got to do it day to day, and that's where habits take over. You fall back to old habits, and you realize 6 months have gone by and you hadn't written a test for 3 months. Where did it all go wrong? Well, if you haven't developed a habit, you don't know how to develop a habit, that's going to be really, really hard. So we're going to look a little bit about the very sort of general principles of habit forming, and then specifically how we can tailor that to adopting TDD in a way that's going to accelerate the whole thing. Related to that, but a subject in its own right, something I call dopamine triggers. So we'll look at what dopamine actually is and how it relates to all of this, and can help with our habit forming. And an area that I call externalizing your brain. Using TDD to have a bigger brain, basically, by offloading a lot of it, to free us up to work on other things. So we're going to look at those 3 areas. Before we get to that, I want to come back to the technical side of it and make sure that we all on the same page about what TDD actually is. So it's not going to be a general introductory talk on TDD, but I want to cover it just enough that we at least know the fundamentals. So I'm going to go into a tale of 2 cycles. I'm going to look at 2 cycles. Now, this is also an excuse to get a photo of my kids up. This is actually about 10 years ago. They're a bit bigger now, and so are their bikes. But nonetheless, you can see 2 cycles there. They're not the ones we're going to talk about, of course. The first one I want to talk about is the TDD cycle. Now, if you have looked at TDD before, this should be familiar. You've probably heard of it anyway. Sometimes known as the red-green refactor cycle, after the colors used. Apologies if you do have trouble distinguishing colors. They're not strictly necessary for understanding this. It's just a metaphor. But the red-green stages have the color. I've just colored the refactor bit, sort of orange or amber, to complete the traffic light metaphor. But this is the TDD cycle. You've probably seen something like it before. This is my version. It's got a couple of extra bits in my version. So how does this work then? Let's say we're going to make sure we're all on the same page on this. TDD itself is really simple. Right? It's all here on one slide. Mastering TDD there's a lot more to it. But I can at least explain it to you. So you always start with a failing test. Keyword there is, well, two keywords. Start, that's the bit that's often missed. If you're going to start with a failing test, it's not TDD. And it has to be a failing test. So if you write a test and it passes first time, that's not part of the TDD cycle. That doesn't mean that it's wrong or bad or something you should avoid. But just be aware, it's not part of the TDD cycle, and sometimes there are consequences to that. We'll look at that in a minute. We're going to look at a code example. To be part of the TDD cycle, you have to start with a failing test. But the word test can be a bit more woolly. It doesn't have to be an assertion and a test framework. It can just be a compiler error because you've written some code, makes a call that doesn't exist yet, uses a class that doesn't exist yet. And then you have to write that code to make the test pass. That's part of the TDD cycle. That all works. And you can generalize that even more. And this is where we start to get into test-driven thinking. It's not even necessarily about the code. The more you do this, the more you start to see these patterns in more and more things. You think, I have to set the expectation, have something that gives me a signal when I know that it's met. There's my test. And you can apply the same things. But let's just keep it to the code for now. We've got our failing test. Then and only then do we move on to the green stage. Write just the code to make the test pass. Again, I've highlighted the word just. So another subtlety. Part of the reason we want to do TDD is we want to have like nice clean code, well-factored code, design principles come into it. But we don't do that here. That's not the purpose of the green stage. We want to write just the code to make the test pass. Simplest thing that will work. I mentioned earlier, many of us started as hobbyist programmers. Hacking code, seeing what works. Brings back a bit of that sort of mindset of, how can we just get this to work? Quickest thing. Now, if that was the only thing we did, we would soon end with a big ball of mud. I'm sure we've all been there. That's why we have the refactor stage. Only when the tests are all green, they're all passing, can we move on to the refactor stage. And that's where we can then apply our clean code principles, design principles, factor our code well. It's not just about, there's a book, Refactoring. Chris Oldwood made a joke about it the other day. There is actually a second edition. It does have new content. But it's not just about that specific set of refactorings, although that is very valuable. But this is where we then change the code to have a better design. Same functionality, better design. And we can get it back to a working state if we've broken it, because we know that the tests are there to show us. One of the tricky parts of the refactoring step is we often don't do anything there. We don't have to do anything there. So we'll go around this cycle a few times, skipping the refactoring step, and then we forget. And then we can end up with that big ball of mud. So that's one of the tricky bits we need to keep in mind. Once we've done that, and we're all green again, we get this extra stage. This is not usually part of the cycle. I like to put it as a separate step, just to ask, are we done? Do we have another test to write? Do we have another feature to add? Might seem obvious, but as we'll see later, there's a difference between asking the question here when we're just about to write the next test, and asking it when we're sort of down deep in the code mines, hacking away at code, because you have a different mindset. So I like to separate it out. And then either we go around the cycle again or we're done. And that is TDD. So thank you very much. No, there's more to it. But that's all I'm going to say about the process for the moment. Yeah.
Why did we decide after refactoring and not before?
Why do we what, sorry?
Decide whether we are done after refactoring
okay.
and not before.
So the question was, why do we ask the question, are we done after refactoring and not before? Bear in mind, you don't necessarily need to do anything at the refactoring step, but if you do, it's because the code's not in the best, most well-factored state. You know, it may have some problems, design problems. So we're not really done until we've addressed those. We're done when we left it in a clean state. But we'll come back to that a bit later when we talk about the mindsets. Thank you for the question. Any other questions on this before we move on? It's probably a good time to log those in. Okay, let's carry on. So I want to just establish this a bit more with a worked code example. Now, I've prepared it all on slides, but I tried to give it a live coding feel. I think that tends to work better. So the example I've chosen to do, this is what we call a coding kata, where you just sort of practice a very simple example to just as an excuse to try something else, in this case, TDD. So the problem itself is not challenging, but it's just challenging enough that you have to think about it. And the one I've chosen is left pad. Who remembers the incident with JavaScript a few years ago where the left pad library was pulled from NPM, and it turned out that half the internet transitively depended on it and all suddenly stopped working. And we said, well, why does half the internet depend on this tiny little library that anyone could write themselves? Well, let's do that in C++. So, of course, we're going to use catch 2, mentioned earlier. It's the framework I wrote. Really, all you have to do is include the header file. Actually, it's slightly changed a bit now, but we'll brush that aside. This actually is a fully working program. It doesn't do much, but it does tell you that no tests ran. That's feedback. That tells you that you've got it up and running, sort of working end to end. Doesn't do anything, but now anything you add on top of that, any problems are because of what you just added. That's an important principle. Okay, maybe you're not convinced yet, don't worry. Let's add a test case. So, nice thing about catch is test names can be free-form strings. If you're used to other frameworks, that might look unfamiliar. So, here we're just putting the description of what we want to test as the test name. We want a function such that strings can be padded to the left. It's a bit vague. Maybe you could do better. But that's what we're working to. And actually, we can even run that. We get now some different feedback. Baby steps. It's a really important principle in TDD. Every time you can check that the thing you just did has some feedback that's different to the previous one, take that baby step. Because then when something does differ to what you expected, you know it's only because of that tiny little thing you just did before. Really important. Which does also mean, and this is particularly important in C++, you need an environment where you can get that feedback quickly. If you have to wait for a 45-minute build before you get this message, that's probably not going to be a very comfortable cycle. So make sure you can get this like within a second or two before you start. Another reason, take these baby steps. You'll know when that starts to go wrong. Okay, so nothing too interesting yet. But actually, we can do better than this with catch. And you might not always do this, but if you run it with the -w no assertions argument, then it will say, well, we've got a test case, but it's got no assertions. That's now an error. Right? So we've made this into a failing test. Right? We've gone one time around the TDD cycle. A little bit extreme, but it can be worth doing this sometimes, especially if it's in a new environment. Okay, all right, let's fix that always succeeds. Yep, I'm stringing this out, but this is the real thing. Okay, let's write some real code. So, require is the assertion macro in catch. And we're going to require that when we call a function called leftpad, we give it a string and a string length, and we're going to get back a string. I've got empty strings, zeros. This is what we do in TDD. We always start with the simplest possible values, which are empty strings and zeros and empty containers, null pointers, any of those things. That will serve two purposes. One, it often flushes out edge cases, simple edge cases that you might not otherwise think of. And secondly, it helps us to keep that baby steps regime. The smallest possible increments, having failing tests along the way. One of the big challenges of TDD is being able to write that next failing test without making a big jump in functionality. The way we do that is we start with the simple values and we progressively ratchet up to a more complex value, a variable, a conditional, and so on in complexity. We're going to see that in practice in a moment. But this is a test. And it's a failing test because it doesn't compile. Just say the compiler access your test framework here. C++ is a static language. We can use that. Statically typed language. So use of undeclared identifier leftpad. We haven't written leftpad. We don't even need to compile it these days. Most compilers will just highlight the code for us in red. That's fine. That's your signal. That's that failing test. So let's write a leftpad. Now, here we're just returning an empty string. But we've flashed out the signature. We now get it to compile. Trouble is, if we run that passes. Why is that a problem? I mean, we had a failing test before, now we've got a test that passes. That's right, isn't it? The tricky bit here is that we actually wrote two tests. The compiler error was the first test. Getting it to compile was passed in the first test. Right, now we've got a runtime test. And the runtime test also passes. So this one passed first time, not part of the TDD cycle. Can we do better? In this case, we wanted to start with the simplest possible value in the implementation code as well, also an empty string. Well, one of these two we're going to have to change to be incorrect. Either we return a different value from our implementation, or we test against a different value in our test code. Which one should we change? I'm not sure there's an absolute answer here, but my thinking, my approach is that the test code should always be correct. Right, I've written a correct test, I want to make that correct test pass. Whereas the code under test is under evolution. We are evolving it to be in a correct state. So along the way, I can make it deliberately incorrect. Something like this. Return some non-empty string, and now it compiles, but we can now get the runtime failure. And then we can see some feedback. We can see we've got an X instead of an empty string, exactly as we expected. Baby steps. Great. Because sometimes you're going to do this, and you'll get something different here. You think, oh, actually it passed, and I expected it to fail. That's new information we can act on. Okay. Now we can go back to the empty string implementation. We've got the passing test. It still seems a bit odd, though. I mean, we know we want this function to do more than return an empty string. So why do we start there? Right, this is one of the hardest things for a lot of people to really get their head around, why we do this. But really, it's all about how much we can get out of those baby steps and how many tests we can write that fail, and then we write the code to make them pass and see that transition. So we know that every test we've written is testing a line of production code. And every line of production code has a test for it. And we can only do that if we do this sort of lockstep, baby steps approach. So we start with a simple value. And that now says, well, I know that's not the implementation, so I now need to write another test. So let's write a test that passes a non-empty string. Keep the pad length string value 0. And now, of course, it fails, as expected. We have to write a little bit more to make that pass, so we can return the string that we passed in. Now, both tests pass. Of course, we have to keep all of the original test passing as well. All right. We're not there yet, of course. Forces us to write another test. So this time, we have, let's go with an empty string and a non-zero pad length. Right, should give us an empty padded string. Fails, of course. Yep. And now, we have to make our implementation code a bit more complex. We've introduced a conditional. The interesting thing here is the first branch of the if here is the same as the code we had before, which means the else portion is now new code, so the same rule applies. Now we return a hard-coded string. So we've got a variable and hard-coded string. We're still not done, of course, so we write another test, and we can see it fail again. So empty string, a different pad length, right? So we can't use the hard-coded string anymore. Forces us to generalize a little bit more. Now there's a constructor on stood string that takes a character and a number of repetitions for that character and gives you a string of that length. And if you're like me, you'll always write it like this, which fails because the arguments are actually the other way around. Yeah, who here always does it that way? A few hands. The test caught it. That's a nice result. So here's an example of a test that we sort of expected to pass, but now it fails. Doesn't happen that often, but it does happen. Great, that could have been a nasty bug left in production. All right. So we switch them around, and now they all pass. Great. Now, already at this point, we're only 4 tests in. When I use this example in my TDD classes, I'd say about half, maybe more, of the groups that I have doing this, they will have already had to write 1 or more tests that passed first time. So they didn't follow the TDD cycle. That's why we do this process of starting with the simplest possible hard-coded value, a different hard-coded value, variable, and so on. How far can we push this? All right. Let's now combine a non-empty string and a pad length that's even greater. So now we have a padded actual string. 5 tests in before we got here. Still fails. We're only returning the padded portion. So we just need to subtract the length of our input string and add the string itself on. Another little baby step. But notice we've done that separately from working out the correct constructor for string. So that was nice. It all passes. And in fact, that is pretty much a complete implementation. And I'm struggling to think of many more tests that I could write that would fail first time at this point. So one thing we haven't done is look at that refactoring step. Maybe we've left it a bit long. In this case, I think we've been okay. But certainly once we've got things actually working in the right shape, it's a good time to have a look and think, what can we refactor here? It's not a lot, but there's some things we can do. First of all, that min len minus stra length, what does that actually represent? It'd be nice to get that a named variable. Let's pull that out. That's our padding length, pad length. Little thing, but actually, now we've got that, we could think, well, I've got that if in there, but do I even need that? I could say, well, what if I took the max of 0 and our pad length? Because if it's 0, then our constructed string is going to be empty. And now we can just do it with no if statement, no conditional. I mean, there is one that's hiding in std max, but we haven't had to write it. Is that going to pass? See someone shaking their head. That fails with an exception. Anyone spot what the issue is, by the way? Sorry?
A string of zero characters.
Mike.
Oh, I don't think it likes to create a string of
Less
zero
than zero,
characters.
Yeah, we've got unsigned and signed types being mixed. We're ending up with a huge number, basically, and then trying to allocate a string that size. So in this case, just adding the int on std max will be sufficient. I'm also changing the argument. So out there, min-len, I've changed that to an int as well, because that's just a little bit more honest about the size that we can represent. That does now mean that we should probably write a test against passing a negative pad length. I'd expect it to pass first time, but we should probably write a test for it. So, okay, we caught that. Now I think this is a nice, simpler implementation. We might also want to go in the direction of making this more performant. This might not be the most performant implementation, but it's a good start. That depends on your use. Okay, oh, and of course the test pass. So I'm going to stop there. Simple example, but I think it gives you a flavor of how we approach TDD. It's all about those baby steps and making sure that we maximize the number of failing tests that we can write first. Because every time we write a failing test and make it pass, we're testing one more branch for your code. So if you follow TDD strictly, you should easily end up with 100% code coverage. Trouble is, we can't always follow TDD strictly, but assuming we do, we'll have 100% code coverage. But that's line or statement coverage. One thing that's much harder to, or in the general case, impossible to test for, is branch coverage. TDD, if you follow this approach, will give you a much greater branch coverage as well, as we've hopefully seen. So that's our worked example. Hopefully, even if I've not entirely convinced you, you've got a better idea what it's all about. So let's assume I've convinced you. How do we then carry that forward? That was the first cycle. I said there were two. Second one's where it all changes. Right? We're not in Kansas anymore. So let's look at habit forming. Bit of a change of pace. But as I said, you've practiced TDD, you've done it a bit on your own. You decide, I want to start doing this in my production code, but then you've got to establish a habit. And we already have a habit around writing code that's established. Your habit may be different, but maybe we approach code by thinking, right, I want to write this feature, so I'm just going to hack away at some code until it seems to work. Or maybe you've got some other process, but it's going to be different to the TDD process. And so your habit is going to keep drawing you back to the old ways of doing things. And you're probably going to link that to TDD just being a failure. That's not the case. So how do habits work then? And maybe you've looked at this before, so this might be familiar, but if not, this is actually a really great thing to know about in general, because being able to change habits, build new habits, is a really powerful thing in general. So habits consist of these three things: a cue or a trigger, a behavior, sometimes called a routine, the thing that we actually usually think of as the habit itself, the thing you do, and a reward. The reward is what you get, positive thing out of it. But here's the thing. Once a habit is established, you don't actually need the reward. It's like a program. You're basically programmed to perform this routine given a certain cue. Remember those associations in the brain? You just made a pathway. It's easy to follow. Path of least resistance. It's really what it's about. A lot of these rewards come from another principle that we can draw on, the pain-pleasure principle. You may have heard of that one as well. So, as animals, primitively, we were always motivated to move towards pleasure or away from pain. There are main drivers. We can override it. We have to do that consciously with effort. But subconsciously, we always move towards immediate pleasure away from immediate pain. Immediacy is key as well. And they often drive these. So there was some pleasure, something positive that we wanted at some point that caused us to perform some behavior given the presence of some trigger. And once that's in there a few times, you've gone around that loop a few times, establish that pathway, then anytime you have that cue or trigger, you will perform that routine unless you take conscious action to override it. And it doesn't matter if you get the reward or not. The pattern's established. And once it's established, there's pretty much nothing you can do to change that. You can't change the cues and reward parts of this anymore. What you can do is you can establish a new routine. It has to be done consciously, and you have to identify the cue and the reward. Most of the time when we have a habit, we only think of the routine or the behavior. It can actually be quite hard to establish what the cue and the rewards actually are. So I've done that for you in this case. And it may vary, but it's going to look something like this. The cue will be that you want to write some code. You want to implement some new feature. The reward is, well, you get some immediate positive feedback. You see it working. Or you get, somebody saying, yeah, you did a good job with that. Whatever that reward is, you have to think of that part for yourself, perhaps. But the behavior that you may have had will be, you hack away or you follow some process, but that's the bit we want to change. Right? We now want to say, well, I want to write it with a test. I want to drive it with a test. I want to use TDD. That's the bit we want to change. So really, the key is the reward part. How can we establish the reward in such a way that it's met by following TDD? Well, we already looked at that. So we said that when we perform these baby steps, we see a test fail, we write some code and we see it pass. Right? We see the change from red to green. That's a positive signal. It's immediate positive feedback. But now instead of having to hack away for minutes, hours, days before we get that positive feedback, we'll often get it in seconds. So we've actually increased the frequency of the reward. Right? But it's worth consciously taking that in and thinking every time I see my test framework or whatever we're using, give me that immediate positive feedback. I want to take notice of that. But yeah, that's good. Great. Experience the reward. Tied in to this loop. Associate it with the behavior of writing TDD. That's not the only one. On a slightly bigger scale, you might get to the end of a piece of functionality and think, hey, I'm happier with the way that's turned out. I've got better design code, it's got less bugs, and bigger scale still. This is more maintainable over time, lower defect rate, meeting my deadline sooner. Every time you notice that positive thing, take note of it, associate it with the use of TDD, and it will establish this pattern onto an already powerful habit. And this really works. And in a moment, I'm going to tell you how to take it up to an even higher level. But the important thing here, as I said before, is once you've done that, you don't even need the reward anymore. So you need to become aware of it for a while, re-establish the habit with a new behavior, and then you don't need the reward. And at that point, it's hard not to follow the habit. Which means if you do this, it comes with a bit of a warning. You're going to find it hard to write code without using TDD, which is normally not a bad thing, but do be warned. It also means that you might find yourself getting more creative about how you can apply a test-driven mindset to code once you've established this habit, because you're going to be more motivated to do so. Cases where you might think, oh, I'm going to write that off, I can't use TDD for that, it's too hard. They're going to think, oh no, it's worth the effort now. So be warned. All right. That's the habit loop. Let's look at dopamine triggers. Right, we all know about dopamine, I'm sure. There's a Wikipedia description of dopamine. It says, in popular culture and media, dopamine is often portrayed as the main chemical of pleasure. And that's what we usually associate it with, feeling of pleasure, reward for doing something. But it's not exactly what this says, which is interesting. It says, in popular culture and media, it's often portrayed that way. So does that mean it's not the main chemical of pleasure? Well, it is related, but there's a bit more to it. If you read on in Wikipedia, it says, but the current opinion in pharmacology is that dopamine instead confers motivational salience. Okay, what does that mean? Well, let's break it up. So motivational, that's easy to understand. We talked about motivation in the context of the habit loop as well. In fact, just the word motive from motivation, conveys a sense of movement, motion towards pleasure, away from pain, as we said. So we can see how that all fits in. What about salience? If you're not familiar with the word salience, maybe think of the word salient, like the salient facts, maybe more familiar. The salient facts are the relevant facts, the important facts in a particular situation. Salience is the awareness of the salient facts. So this is really about motivation to find the salient facts, to become more aware of what the important facts are. What's this got to do with dopamine in the first place? Well, there was an experiment that they ran which shed a bit of light on this. As with many of these experiments with trained monkeys, they put a trained monkey in a room with a lever. And every time the monkey pulls the lever, it would deliver a treat. Great. And of course, it's all wired up so they can detect levels of dopamine, and they'll see the dopamine spiking every time they got the treat. That sort of matches this idea of dopamine and pleasure being linked. But then after a while, the dopamine starts to tail off. And after a bit longer, the monkey will stop pulling the lever. It's got enough bananas or whatever it is for now. It knows if it wants another one, it can just go back, pull the lever any time. Right? It knows what the pattern is. That's the salient fact in this situation. So they did another experiment where they only deliver the treat 50% of the time at random. And what they found was the dopamine levels stayed high. And the monkey would keep pulling the lever or trying different patterns. They're trying to establish what the new pattern is, because that's now the salient fact. And because there was no pattern, it was random, they'll just keep doing it. That's what dopamine does. It puts you into a heightened state of awareness so that you can find something that's going to give you a reward, rather than necessarily being the reward itself, which is a really interesting, different perspective on this. Okay, so what's that got to do with TDD? Well, what things in the TDD cycle can give you a reward, but not all of the time? Here's a few examples. We looked at some of them earlier. Right? Seeing a test pass, and you're going from red to green. It happens a lot, but not every time, because sometimes it's going to surprise us. Sometimes we expect the test to pass, and it didn't. Or sometimes we expect the test to fail, but it passed. And when that happens, when it breaks that pattern, well, now that dopamine is priming us for learning, for looking for the pattern, looking for the reason why it didn't follow the expected pattern, which is exactly the right frame of mind you want to be in, yeah? Similar, seeing a test go from red to green. Also that race to green. When you're at the green stage, I said That's not when we're worrying about clean code and design principles. We're just hacking away. Again, particularly if we come from a hobbyist background, that can be fun. Yeah? And that also ties into the pleasure part. Even the refactor step, cleaning code without breaking anything. Yeah, it's that little challenge that you get where most of the time you're going to get it, but then sometimes it still breaks. It's all safe, but you're ready, you're primed for learning again. Why did it break? What did I do wrong? You see the interplay here. But also you can see how that can strengthen the habit loop if you tie this in. So that's dopamine triggers, and I think it's a really powerful way to have more fun and also become more productive at the same time. All right, there were 3 areas from psychology and neuroscience I want to look into. The third one is all about externalizing your brain. So this one's a little bit different, but it's still based on that underlying principle of the brain being a big association machine. That really comes back to how we are wired up as humans. We have what's called an open loop architecture. So we've not evolved to thrive in isolation. Right? We thrive with other humans, part of a group, a tribe, family, friends. And so our communication and thinking styles have evolved in that environment. So we can actually sort of think openly through communication of different forms and establish bigger thinking patterns than individuals. That's this open loop principle. Now, set aside that some people prefer more isolation than others. In general, as humans, this is the way we've evolved. And at some point, we discovered we don't actually necessarily need other humans to take advantage of this. Just being able to write things down actually helps us to offload our thinking so that we can focus on something else without losing track of what we were thinking about. It's still part of that same open loop process. And more recent times, we use computers and other equipment like that to capture our thoughts, write them down. Great productivity tool. And now, you can use TDD as well. How? Well, let's come back to the TDD cycle. Now, we've established these 3 stages, red, green, refactor. Turns out that each of these stages requires a different way of thinking, a different mindset. You're playing a different role. So when you're writing a failing test, you're thinking about high-level design, requirements, user experience. What's it like to be a user of your code? And how does this relate to what the problem is that I'm trying to solve? Yeah? And then, that's where the magic happens. Remember I said, encode your expectation? We write that down in code. And not just written down like on paper, but we've written it in code that's going to tell us when that requirement is now met, that expectation is met. It frees us from having to worry about that anymore, so we can seamlessly switch to a different mindset. Because over here, at the writing the code to make the test pass stage, now we're implementing. We're not worrying about requirements, we're not worrying about design, we're not worrying about any of those things. We just have one goal, and that's to make this test pass. And we can bring different resources, different mental resources to this problem. And it's a really powerful switch as well. I mean, I'm sure you've had the experience where you come into a room to look for something, and you can't remember where you came. You go back to where you came from and you remember because of the contextual clues. They can be really powerful. And if you're in the middle of thinking about something, you need to switch in a sort of a very artificial way. That can be really hard. But when you've got these like natural save points, all the thinking you've done is encapsulated in the test, frees you up to now think of the problem in a different way. And then there's another switch. When you go from green to refactor, now instead of hacking away to get the code to the test to pass. Now we're thinking, oh, I just need to preserve the functionality and improve the design. It's the only thing I need to focus on. Right? The test has now locked in that behavior. One thing at a time. It frees us up. And similarly, back again at the end, now we're thinking about design and requirements again. And that's why I like to put the are we done step over here. When we're now back in this requirements mindset, we're thinking about what do I actually need to do rather than what I could do. And there's a Jurassic Park quote in there somewhere, I'm sure. So this is how externalizing our brain works with TDD. We externalize it into the code, into the tests, and then into the implementation and back. And this doesn't happen straight away. It takes a little while to get used to this flow. But once you do, you'll start finding that you can make these transitions very quickly. I mean, the whole TDD cycle can often last seconds. And in those seconds, you're playing different roles, seamlessly switching. Notice those things because it actually helps you to accelerate them. So that's externalizing our brain. And that's the third of those three areas from psychology and neuroscience I wanted to look at. So let's see how we stack up on these things we looked at earlier. Well, the fun and keeping you focused, well, they're what we just looked at. You know, the dopamine, the hacking away, freeing us up to just work on one thing at a time. That all contributes to these things being fun. There's a bit of gamification in there as well. Keeping you focused on what matters, well, that's the externalizing our brain part. Yeah, you're focusing on one thing at a time rather than having to make these mental switches artificially. It's a much more natural experience. But what about these? I mean, surely it's still extra work, isn't it? Still going to slow you down. Well, let's dig into that just a little bit more. You've probably heard of left shifting, shift left testing. I actually traced it back to this article from 2001 by Larry Smith, Shift Left Testing, in Dr. Dobbs' journal. Anyone read the original article? No. But I'm sure we're all familiar with the term. Actually, the idea itself is even earlier than that. I think that's just the first use of that term. I first came across it in this book, and this is the 1993 edition. There is a later edition as well. Code Complete, Steve McConnell. Who's read this book? Handful of people. It is quite old now, but still entirely relevant, I think. Now, in there's this chart. And you've probably seen something like this many times, but different stages of the software development life cycle. And the cost of change or the cost of a defect at different parts of that life cycle gets more expensive, particularly in money, but also in time, the later in the process it occurs. So the idea of left shifting is to move things further back. And particularly with testing earlier means that we reduce the cost of finding a defect. So just from that alone, we could say, well, if we're testing before we write code, then it must be cheaper than testing after. It's the left shift. But we can go further than that. I want to ask a question. And I can't remember if it was Kevin Henney or John Jagger I originally heard this from, but I'll credit both of them. I think one of them got it from the other anyway. Why do cars have brakes? And when I'm doing a class, I'll actually ask the question and expect a response. But it's obviously a trick question, so you're thinking, what's the trick? But the natural response would have been something like to stop or to slow down. But in fact, it's so we can go faster. Because how fast would you drive if you didn't have brakes? Not very fast at all, I expect. And if that's not your response, then please don't give me a lift home. The metaphor is obviously with testing. You know, we don't have tests to slow us down. We have tests to speed us up because they will stop us if we make a mistake. Right? We can move faster because we have less to worry about. We can also move faster because we have a better design, and we haven't had time to get into design today, but that's a big factor as well. If we have a better factored design, refactoring leads to better factored code. It's easier to make changes, faster to make changes. So lots of reasons, but this is one of them, that we will end up being faster overall. We avoid rework, we avoid chasing down bugs later, and when we do have issues, they tend to come up earlier, where they're cheaper to fix. So that's how we can rewire our brain with test-driven thinking in C++. Some references to other material on my site, levelofindirection.com/refs/rewire.html. So rather than putting up a whole set of references, you can go there. If this URL is too hard to remember, I've also got extra level of indirection that redirects there, of course. Or you can find me one of these places or catch me afterwards. But that's the end of my talk. Thank you.